Hey everybody, welcome to Super Simple. I'm Marc Teer, the founder of Black Spectacles, and today we're very lucky to have Heath May from HKS join us. We did a sort of a little bit of a preview a couple of days ago, and trust me, you guys are in for an awesome project. Some of the things these guys are doing are really at the bleeding edge of what's possible in architecture, so this is going to be a really awesome one. If you don't know Heath, he's a director of HKS Laboratory for Intensive Exploration. He's an architect with 12 years of professional experience, including commercial, hospitality, sports, and healthcare. He's currently focused on R&D and the application of this research to the built environment. He has an avid interest in passive solar design, which encourages current line of research initiative into the potential for using software for dynamic solar design. In addition to R&D, Heath leads a design team responsible for projects including Future GSA, which is a net zero renovation solution that earned the 2012 WAN Commercial Building of the Year award. And he worked as a senior designer on sustainable urban living, which was a winner of the 2010 Chicago Athenaeum Green Good Design Award. In April of 2013, he was named a recipient of the Building Design and Construction's 40 Under 40. Way to go, Heath. And he currently serves on the advisory board of the PACCAR Technology Institute at the University of North Texas and holds a position on the executive committee of the HKS Global Design Council. So that's a little bit about Heath. Before we get started, if you'd like to register for our next episode of Super Simple, you can go to blackspectacles.com/podcast to register to attend. And today, you guys know that we have design software tutorials taught by world-class architects like Heath on blackspectacles.com. So make sure you stick around until the end of the episode because we have a special Black Spectacles promo code to share. So stay tuned to hear about that at the end. And then today we'll be taking questions using the GoToWebinar question box, as well as on Twitter using the Super Simple podcast hashtag. So to get started, again, thank you, Heath, for sharing your work with us. Can you tell us a little bit about the LA Rams project?
Thanks, Mark. Yeah, so what we have here, we have a 70,000 seats NFL stadium. It's part of about 300 acres of urban redevelopment in Inglewood, California. It's just east of LAX. Roughly 11 acres of open plaza that will be covered by an aluminum skin. And a 6,000 seat performing arts venue also underneath that aluminum skin. So the premise of the project, really large redevelopment just east of LAX airport in LA. You know, the thing I want to mention first is that this is very much a work in progress, and as you can imagine, with a project of this scope and complexity, it's a very highly orchestrated team. And so, I want to particularly thank Walter P. Moore Engineers, Zahner Metals, and Studio NYL as being really key players and part of the process with our sports and entertainment studio, along with Line here at the office.
So this is it, right?
That is it. So here we have just an aerial kind of to get your bearings a bit. So the roof that you see here is covering not only the NFL stadium itself, but that 6,000 square foot performance venue and a really large area of public plaza. And it's important to understand that this is an open air stadium, so while we have some protection from the elements, it's not going to be enclosed and air conditioned in the traditional sense. Okay. So go to the next slide here. Before we get into exactly what we're doing, I thought it would be helpful to understand kind of why and how we approach this project. And we use technology early in the process to really kind of understand the climate of the location, and we dig really deep into this. And so this is kind of a page from what we call a design brief that we created really early on in the project to start to understand what the climate was like, not just generically in Southern California, but specifically in this site. So we'll go to the next page.
Okay.
And here we can see the outline of the available acreage that we're looking at here, and you can see LAX kind of in the lower left of this page. Okay. So we can understand that it's going to be highly visible from a flight pattern. As you fly into LAX, you're going to come right over the top of the stadium. That was a constraint and a criteria that we had to think about, not only keeping the stadium low enough for the flight patterns, but also thinking about during the construction and the erection process how we make sure to keep the cranes and the other equipment within the FAA guidelines.
Okay.
So early on, what we like to do is look very specifically at a few things, and those things are or include the dry bulb temperature, relative humidity, the wind, and the solar radiation. And by understanding these things, and not only how they work or operate in isolation, but more importantly how they operate together within a system, we can start to really kind of take advantage of this Southern California climate, and we can use strategies developed to allow us to use kind of the natural temperature swings, the natural humidity swings, and the breezes to make this a very comfortable place for people without having to use a lot of HVAC.
Okay.
Okay, so kind of walking through this a bit, one thing that was important as we started to analyze the site is understanding that this particular location was really right on the boundary between two different climate zones. And we'll kind of understand why this is important as we move through these slides. So we go to the next one. We can see that we're right on the edge of California Climate Zone 6 and California Climate Zone 8. And so we're really getting a bit of the more Mediterranean climate that we see along the coast, along with some of the climate that's a bit different further inland. And we have to kind of take both of these things into account, because understanding these allows us to develop the right strategies to create kind of this open air environment that will be comfortable.
Okay.
So next slide. This is just the Köppen-Geiger climate classification system. It's one of the primary ways to classify climates, and just kind of understanding there, you see the two different climate classifications and kind of how we straddle the boundary between the two. And then in the next slide, we're looking at some PRISM climate data. These are 30-year normal patterns so that we can start to kind of understand the annual precipitation. That's part of what we're studying, along with a lot of other climate. We look at typical meteorological year, TMY3 files. And what we started to do is actually use some other services that project the climate into the future, because we know that we live in a time of really rapid and remarkable climate change. Mm-hmm. And if we're designing based on what's happened over the past 30 years, we're really kind of starting out behind. So we've started to project that climate data as well.
Okay.
And then just a few images of things that we're using. These are coming out of Ecotect. You know, it's a very readily available software, very powerful if you know what to use to generate the information, and how to understand the information that's coming out of it. So here we're looking at the dry bulb temperature through the year and through the day.
Okay.
And the next slide will help us understand a bit about the prevailing winds, and we're really interested in not only what direction they're coming from and what the magnitude of that wind is, but the content of the wind itself. And so what is the temperature, what is the humidity, and if we can understand these things, we can really start to synthesize a lot of these different climatic variables to help us with our strategies.
Okay.
So psychrometric charts, and so most architecture students see these at some point in their education, but essentially we're looking at temperature and humidity, and we're plotting all the points during the year and kind of understanding what is the climate like in this zone relative to what a person in North America might feel comfortable. So that kind of darker blue area, that indicates kind of the zone of human comfort, at least within the culture of where we live. And we can see that a lot of the points during the year are at a lower temperature than what we're usually comfortable. So we kind of have to understand that we need to employ strategies that allow us to expand that range of human comfort, both directions. So you can see here, thermal mass effect is something that we can use, where we can retain some heat and we can release it later in the night when we get a diurnal swing, so we can bring the temperature up and have it to be a little more stable.
Okay.
Next slide. And it's just important here to show two of these, because throughout this process of studying and analyzing the site, we had to pull data from two different airports. We needed to get one that was in both climate regions, and what we found was that data was similar, but there were enough differences that it made it very important for us to look at both sets of data and do some analytics between.
Okay.
Okay. And the next couple of slides show how we start to look at the LA Basin ecology and start to understand what are the natural features and the different variations in local flora and fauna. These things can often be overlooked when we're designing a project, because many times an architect has a tendency to jump straight into design without really understanding what's available. But if we go to the next slide, we can start to see where our project sits, that little yellow indicator in the lower right, and then we can look at some of the different environmental regions that are kind of around and surrounding LA, and we can understand that there's the chaparral region that's really quite intense in terms of the wildlife, both with plants and animals. And in the next slide, something that we've started to do is we really try to take an inventory of all the native plant species. And what this allows us to do is kind of understand going in what would be appropriate to use here and how can we use this for things, something other than just thinking about it as a static landscape, but we can kind of take advantage of the evapotranspiration these different plants and understand how if we can drag a breeze across a certain species that might help to cool the air or provide a different humidity level.
Okay.
So next slide, we establish a strategy, and our strategy is really kind of based within something called systems thinking. And systems thinking is really kind of understanding patterns or relationships between two things and how those could translate into behaviors. And so when we employ a strategy based on systems thinking, we build in what I call relational redundancy. So we create a system that's not going to fail if one particular point of that system fails. We have something that's more ecological in design. And the next slide starts to show visually laying out how we work with the design team to understand the client's goals early on. So what we have here is kind of goals and strategies, and we had a goal of kind of managing or enhancing the microclimate here to have human comfort and maintain kind of homeostasis where we didn't get any wild temperature and humidity fluctuations. And so what we've tried to do there is really kind of map these to these primary, secondary, tertiary, and even these micro strategies within several different categories and kind of map how each of these things start to talk to each other.
Okay.
So understanding that, that kind of gives you a bit of the why. And so what we were challenged with now is essentially creating this large envelope that does provide this open air environment, and then figuring out how can we make it work. So here's a view kind of looking across from some of the plaza area. So you see that this roof or this skin really covers, as we talked about, more than just the stadium, and it reaches out and creates these kind of outdoor rooms, which are really nice to kind of blur the edge between inside and out. And so now the problem becomes something that's a little more pragmatic. If we go to the next slide, we're going to see what we're looking at is how do we design, develop, document, and fabricate a system comprised of over 75,000 uniquely sized and perforated panels. So what we're doing here, yeah, exactly, super simple. What we're doing here is we're really trying to determine a way to allow us to create a perforation pattern that really starts to give us the visual of an image that we've applied over this entire roof project. And so we started with an image, and this was based on this this microscopic kind of abstraction of something that we found in nature that was very important to the project, and we needed to find a way to map that or to apply it to this panelized system. And the panelized system was really a way to rationalize the non-Euclidean geometry so that we could kind of wrap the entire project. So what we see here is a rendering of some of the triangular panels, and we're going to kind of go into to what we did to rationalize the system.
And maybe, Heath, if I may sort of back up a second. So all the work you guys did to understand sort of the parameters of the site that we just talked through, give me a high-level overview of how does that reflected in this skin that you've created? Because you said from a programmatic standpoint, this big sort of roof piece is designed to sort of kind of bring it all together, both the stadium and these other parts. But how is the sustainable and the site characteristics reflected, I guess, maybe in this piece?
Mm-hmm. So with the roof enclosure itself, we have a combination of this dual layer permeable metal skin system that allows breezes to come in underneath and also filter through.
Okay.
And then the kind of localized area, if you recall back from one of the first images, over the stadium itself, we're using an ETFE skin system as the roof, and we're using that not only because it's lightweight and it's transparent, so we get the feeling of kind of being outside, but we can also kind of use these strategies in combination so that we can kind of tune the ability to bring natural breezes and ventilation in from the side, and then take a little bit advantage of allowing some of the heat that we get in terms of solar heat gain to come into the space to collect in some of the concrete areas.
Okay.
And we can use that thermal mass effect that we talked about to start to radiate that heat later in the evening when it gets a little bit chilly.
Okay.
And so by a combination of being able to trap and retain some of this heat, but have the ability to vacate that very specifically, we're starting the space to work well with its environment.
Okay, so for example here, if you can see this slide here, so this little gap right here is sort of allowing breezes to sort of kind of flow through the hole, underneath the whole roof, and then maybe concrete areas down here, as you say, they're holding the heat, and then later on they're sort of radiate them out. And then also you said you're using, if I followed you right, that this right here, this is ETF material, and so it's allowing you to get natural light in. Am I missing anything there? Is that a good understanding?
That's pretty simply the way it works. We're using a combination of thermal mass, of natural ventilation, and kind of making the two work together really well.
Cool. And then so this roof piece that we're seeing here is what we're going to kind of get into right now. So I'm noticing in this rendering, and renderings change over time, so maybe it's not the case, but is some parts of this roof, maybe they're solid, and some of them are more what we're going to talk about, where they have the perforation. Is that true, or is this entire silver thing have that perforation going?
So the entire silver area will actually have the perforation. At least that's the intent where we are now. I think what we're seeing here is kind of a limitation of being able to render the perforation with the mass beyond. But yeah, where we are and what we're seeing today, really it's kind of a snapshot of where we are, and we've looked at many different ways to solve this. So.
Which is a good question. I mean, where are you guys in the whole process of making this building happen?
Yeah, so essentially where we are right now, what you're seeing is kind of a snapshot in time in terms of one way to resolve this the skin, which is really probably the most complicated part of the project itself. We're in the process of challenging ourselves to think of other ways or methods that we could do that could achieve the right results and be able to meet our budgets and our time constraints and still maintain what we set out to do in the beginning. So. Okay.
Are you guys under construction right now, or not quite yet?
They are moving dirt and have begun a lot of the initial phases for the overall development there on site. So if you go out there today, you can kind of see that underway. And where we are with everything else is really kind of getting everything ready to go. We're targeting a 2019 open date. So as you can imagine, it's getting really close.
Sure. Okay. Cool. So let's hop back to the. What are you guys calling this? Are you calling this a roof? Are you calling this the skin? What are you calling it?
Yeah, it's we've kind of called it the skin, just because it does kind of shoulder around and kind of do a couple of things.
Cool.
So the roof problem here that we're looking at. What we wanted to do is we wanted to, rather than design something and come back late in the process, late in DD or even CDs, and start to work with a fabricator at that point to kind of resolve all the challenges and to maintain what our architects like to call design intent. We decided it makes a lot more sense for the way we work to really kind of deliver that design intent through an understanding of the fabrication process. And so we worked really early to start to understand available materials, available processes, and different equipment on the shop floor so that we could really kind of build some intelligence into the system based on what we were able to accomplish. And so what we're seeing here with these perforation constraints, this is kind of funny when you look at it, but essentially we're constrained more by time than anything else. It was determined pretty early on that we can go two routes when you're rationalizing a surface like this, and one of them is to create a a modular piece. And so we could say we're going to have one triangular element that will comprise this entire skin system. And that's certainly a way to do it. And quite honestly, in traditional kind of construction methods, that made a lot of sense for many years. But now, with the ability for mass customization and with new fabrication techniques, the way that we were going to cut the triangles and to punch the perforations, really, it didn't save us a lot of time to make them all the same size. And so what we're looking at here is how can we meet the time limitations. And so we determined that based on the available machinery and techniques that we had in the open date not moving, we could use up to 8 hole sizes to achieve this perforation pattern. And we needed to keep these perforations under 52 million. At that point, it was going to be really hard to kind of meet our schedule. And then the material constraint, based on the gauge of the material and the type of material, we needed to maintain greater than a ½ inch of spacing between the holes for the structural integrity.
I like that. Only 52 million holes. How's that magic number come out? Did you find out that it takes so much time to punch a hole, and you have a certain time in your schedule or something?
Exactly. It's about as simple as that, as pulling out the calculator and kind of backing the hours in the years and understanding if we have X amount of seconds per hole. We can extrapolate that and understand how many we can punch. Yeah.
That's awesome. Okay, cool.
Okay, so the detail that we talked about, so these perforations that are creating this overall visual image and allowing for this kind of permeable facade, those are going to be punched. And so what we're looking at is kind of the detail of the coined die punch. So there'll be various sizes, but they will be punched at the same machine station where the triangle is actually cut around the perimeter.
Okay.
Panel constraints. So again, where we are today, what we're looking at is we're keeping each triangular panel less than 4 feet in width and with less than 10 degrees variation from equilateral. And we're trying to maintain kind of a consistent material grain with understanding that this particular aluminum in the finish that we're looking to use, that's really kind of a visual constraint to make sure everything flows really nicely. And I will say here with the constraints, we've looked at upwards of 6 to 7 foot panels in other systems. This 4 foot width constraint is really kind of a product of working with Zahner, with the fabricator that was working with us as a design assist through the better part of this process, and using their proprietary ZEPS system. And so those 4 foot triangles, panels, work within that system. And so everything that you're seeing today is really kind of based on rationalizing to that 4 foot width. Okay. So to start this out, here's a place that you can start to see a shot from above, and you see the ellipse on that left image. That's really kind of the zone of the ETFE where you see these kind of cutouts. So there where your cursor is, and then again down lower. The first thing we did is we needed to kind of set out our primary structural system. And so working with Walter P. Moore, we began by doing this. Portion of it is kind of a radial system that you can see is following that ellipse. But then since this isn't really a symmetrical shape, that radial primary structural grid system starts to kind of slowly fall and evolve into different configurations. And so we get our primary structural system set, and then the next step we need to come in with some of the joist framing and kind of understand, okay, how does that work layered upon this primary structural system? And then the far right image you're seeing there is really more of the tertiary structural framing that's actually going to carry the panel and the panel loads themselves. And so as you can imagine, if we're trying to juggle being efficient with the tonnage of steel, working with seismic considerations, and think about our schedule and our cost, it's kind of a juggling act between how many individual pieces that we have that we're erecting, the size of those pieces, the spans that we're using, and then just the fabrication time. So there's kind of many balls in the air that we're juggling between the structural team, the fabricator, and the design team.
Okay, and just to be clear, as you said, the structure that you're seeing here, this is the structure that's supporting the panel. So it's sort of the substructure that is then attached to the primary structure here over on the left. Is that right?
Correct, exactly.
Cool. Okay.
And so the interesting thing where you could see that, if you want to flip back really quickly to that that panel structure that you were notating there.
This guy?
Yeah, there. So that's something that we have to think about, because even though this is at least as of now, there are two layers of this skin system, one on the exterior and one on the interior. We know that that is going to telegraph through because of the perforation ratio that we have. And so since we have kind of this this visually permeable skin system, we have to kind of keep in mind that this structure is not something that's going to be hidden, you know, in a closed plenum. And so that's something that has to work very very well with you.
Okay, so there's essentially a sandwich here, and the top and bottom of the sandwich are the aluminum panels, and you're just saying since they're perforated, you're going to be able to see everything in between, because there's maybe not that much depth between them, plus you'll have sunlight coming through them, basically?
Yes.
Yeah, okay. Cool, so here was the image.
All right, so the image, you know, so we touched briefly on the idea that that there was this image that was driving this overall perforation pattern. So
actually, Heath, you know what, if I can interrupt you, I'm sorry. I have a question here, which is probably a good time to ask it. Folks are wondering what software was used to create the overall design of the project. So was this a Revit project, is this a Rhino project, is this an ArchiCAD project?
So we began the initial conceptual massing and modeling within Rhino and Grasshopper, and so we tried to set out from the very beginning a way that we could easily share scripts, Grasshopper scripts, between the structural engineer and the design team. And we've kind of learned, as we've done some of these NFL stadiums over the past few years, that having a good computational strategy up front could really help in I think of efficiency not so much as like how quickly we're arriving at a solution, but more about how many different solutions can we explore, and how well can we arrive at the right one. So we tried to set up a computational strategy that began with Rhino and Grasshopper. Very quickly, that included a lot of Python scripting along with the Grasshopper, and at some point in the process, it became very apparent that just the bottleneck of the geometry, because of the scope of this project, you know, these are things that that we've all been doing for several years, you know, kind of managing this complex geometry, but the sheer scope that we were looking at, just the computation time to be able to compute these things, and then to kind of get that data, that information from one person to another, really required that that after the Grasshopper and Rhino and the Python, we went into a C++ environment with Visual Studio and started to create a lot of these procedurals within that environment that would allow us to kind of keep the bottlenecks in check, so that we could have this pipeline of geometry that could be delivered in different formats.
When you're talking, I'm guessing maybe you're, and correct me if I'm wrong here, you're primarily talking about this skin, I think. I'm curious about the entire project, you know, the actual stadium part, sort of the guts of everything else. Is it sort of a hybrid between, you know, let's say Revit and Rhino/Grasshopper, or?
It is, yeah, and that's kind of the way we approach these. Is that Revit it's a very powerful documentation tool, and you know, and for certain things it can be you know, I think the right platform for some of the design consideration. And so a lot of the bowl design work that we're doing for the seating bowl, that's kind of within the Revit platform, and then Revit becomes kind of a container for all of the information, so that we can understand between different parts of this really, really large team that includes not only people at HKS, but other consultants as well. It becomes kind of a repository or container for the geometry at large for the different parts and pieces. So what we might be working on within Visual Studio or within Rhino and Grasshopper will at any given time be represented in some way within this Revit model that kind of houses all of the info.
Okay, cool. So I just wanted to take a minute to sort of talk that through a little bit. So back to the image.
Yeah. So going back to the image. So you know, early on, the design team had this idea that this microscopic image abstracted really could create this this kind of beautiful visual of a perforation pattern over this entire skin system. And so as you can imagine, early in conceptual design, it was relatively easy to kind of map this image, at different scales and create renderings that that could convey the idea, right? What became a little more challenging is that when we really, we had some agreement and alignment on the idea from the client and the project team, and then we needed to really start to study it. This image was 15,000 by 15,000 pixels, and even then it needed to be tiled across the surface. And so what became the challenge was actually rendering this or visualizing it in a way that we could see it where our pixel dimension wasn't the size of 5, 6, 7 or more perforations. And so if we couldn't get the fidelity with the visualization, we were really kind of cheating ourselves in terms of what we were actually going to see. And so the challenge then with the image was how can we process this image in a way that allows us to create the visual that we're looking at in a manner that's consistent with physics and the way light's actually working and not a rendering trick, right? So what we started to look at was different dot densities as we're just manipulating the image itself here. And so we're kind of taking this image and we're looking at kind of different abstraction levels. And so obviously the more dot density we have, the closer to the original image it gets. And then the next study, as we move to the next page, we start to look at some halftone procedures to this image as we're processing it, and you can see kind of a zoomed in on the images above, the 3 images, and then corresponding with each of those is kind of an overall, kind of taking this overall starting image and seeing what happens when we're looking at that. So if we start to look at it with different halftone varieties and in grayscale, we can start to see not only what that does from like an overall perspective from very far away, but also as we begin to move closer, what kind of grain or detail is involved.
Heath, I don't understand what you mean here when you're talking about halftones and grayscales. What are you really doing to that image?
So these are essentially, if we were to open up Photoshop and then start to use some of the filters and start to manipulate that, this is essentially what this is. We're using Photoshop and using that to manipulate the image so that we can just see what different varieties of abstraction we can achieve with it. And so you might imagine you could take a picture of yourself, with your face, and you could put it in. And by doing enough of these kind of color dodging, grayscales, halftones, and these different effects, we can start to create something that might still be recognizable as your face at some level, but as you zoomed in or out, it could start to become really abstract and more visually interesting.
Okay, I gotcha.
Okay. So next slide here, we start to see, moving beyond the halftone procedures and processes, we're looking at some Gaussian blur, and then looking at some of these overlays. And so this is really just an example of how we're starting to manipulate the image using different techniques within Photoshop. So we're trying to manipulate it enough that it becomes something unique, so even though we're starting with something that would probably not be recognizable from most anyone that sees the image had we left it the same, it became a lot more artistic and really started to read at better scale when we did manipulate it and abstract it, to different levels.
Okay.
So next slide. And so now here we start to get into kind of back to the physical world again. So we've just looked at the manipulations of the image itself. So next thing we needed to think about was how do we visualize this image on these panels by punching holes in the panels, knowing that we're going to have to work with either an open a punch, a hole, or a field of just the material itself. And so juggling that against the criteria that we have for the triangles, we needed to determine what's the best procedure to lay out the perforations and how will those be aligned. So you can see we're kind of studying here from the left to right. We start with just kind of an orthogonal alignment, but what you see there is we get kind of this stepped edge. So these staggered edges don't really align to the panel very well. In the middle, we use a diagonal grid that was kind of based off of one edge, and so one edge becomes fairly clean, but the other still has the stair-step effect. in the end, or at least where we are now, what we went to is we kind of subdivided the grid. So we took that triangle and we used a series of subdivisions so that we could align the perforations to every edge. So we got a nice clean edge and a nice spacing between the perforation.
Mm-hmm. That makes sense. That ultimately probably means that all the hole sizes, or maybe they're different, or the spacing between them is slightly different in order to make that all sort of shake out and line up on the sides.
Exactly. What we're visualizing here, we're using a single perforation hole size, really to kind of understand what the largest hole we're using. Can we maintain that half-inch spacing, and can we kind of see where our center points are going to be, so that we know as we manipulate that diameter of the hole size, they're still going to fall within this grid.
Okay.
Okay. And then moving ahead, we're looking at perforation density next. And so, as you can imagine, in order to show this image, we need to kind of fine-tune the density of the perforations with the image map itself at the actual size that it's going to be, so that we know that on one hand, if we have too much density, it's going to give us one look. If we take that to the extreme and we make this as few of perforations as possible, it may not give us enough fidelity to work with in terms of the image itself. So you're seeing here from left to right just an increase in density of these perforations laid out on the subdivided grid.
Okay.
Next, we used a noise multiplier procedural, and so this is kind of a noise algorithm like you might have in different photo editing software that we just ran through our Visual Studio. But what this is allowing us to do is, again, to just look at different iterations of how we abstract the image itself. And so what we're after here is we're trying to balance the amount of fall off or the gradient that we see between the pure image, and then applying this noise multiplier, we start to get a little more of the kind of the pixelated snowflake effect that you see on the upper right image. Mm-hmm. And this is important because it allows us to kind of balance the solid and the void in a way that remains interesting at multiple scales. And so as you're flying over the stadium, you're going to read it at a very far distance as you're driving up to it, versus when you're walking around in the plaza, or you actually walk up into the stadium and reach out and kind of touch the surface. We want it to be visually interesting and engaging at each distance. And so down below.
Heath, let me ask you actually, so just to sort of zoom out to 10,000 feet again, what you guys are doing here is these studies here on how to handle the edge, the density, and then also now about the noise multiplier. You're applying, or you're sort of driving these iterations and these studies, not through Grasshopper necessarily, but you're running them through the software that you guys developed yourself. Is that right?
That's correct, and what that software is essentially doing is it's allowing us to use other software such as Photoshop to apply these procedures. Some of the procedures are applied with the the kind of the custom. I don't know if we would call it an application per se, because we haven't developed a UI that we would release this, but it's something that we can work with, right? Mm-hmm. But this allows us to just handle knowing that for each of these that we're doing, we're going to need to do 75,000 of them. Mm-hmm. Kind of understanding how can we apply this, this many iterations of procedures to this image, and then map it to this triangle 75,000 times, mm-hmm. So that everything coordinates. Mm-hmm. So that's really kind of the reasoning that we're using that custom application.
Okay, because you had so many panels that you would have broken Grasshopper, or you would have broken some other tool in terms of trying to process it and do as many iterations on this as you wanted to.
Right.
Okay.
Okay, and so moving through here, we're just going to kind of flip through these to kind of see the progression, but I just wanted to give you a sense of looking at the panel subdivisions. We're subdividing each of these triangular panels, but we're also looking at how we're tiling the overall image by the same token. So across the upper image that you see there, we can see we start with the triangle and we start to subdivide that to different degrees, and that allows us to really keep the perforation patterning aligned with the panel. And then we're looking at the vertex mapping, where we're starting to kind of use that to kind of create some of the fall off between our solid and void. And then the lower left image is showing our overall image and how it's tiled. And so you can see here, this is a 2x2, and if you look closely down the center line of that lower left image, you can see where it's mirrored.
Mm-hmm.
So that's taking that overall image and it's mirroring it for a 2x tile.
So let me ask you, I don't know what when you're over here, when you're talking about vertex mapping display and recursive midpoint, what does that all mean? I don't know what that means.
So essentially what we're doing there is we're kind of, when we divide the upper one with the panel subdivision that says the centroid mapping display, so we're creating a centroid within each of those subdivisions. So if we look at the 16 faces subdivisions, we have a centroid associated with each of those triangles. And down below, where we're doing the vertex mapping display, what we're doing is we're jumbling those subdivisions that we see in the upper level. And we're kind of jumbling those and switching them around in a way that further abstracts that image. And so you could think about it as if you divided that photograph of our face that we talked about earlier into a 10 by 10 grid, and you started to take one of those cells and switch it in place with another one to get a little bit of a jitter to it. That's kind of what we're doing with that vertex mapping.
Okay, gotcha.
Okay, and so as we flip through these, you can just start to see we go from a 2x2 to a 4x4 tiling, 6x6, and we're just iterating, kind of through a lot of these, and really the idea is I call it, I always kind of want to test the threshold of either side. If we tile it one time versus 20 times, just to kind of see how far we can push it, and that essentially gives us our kind of crude solution space. And so we know that, okay, we want to kind of focus on something, that looks visually pleasing in this area, but kind of meets our criteria with everything. And so where we are right now, we're at a 4x4 tiling, and that's taking this image and it's used 4 times across the entire surface that we're seeing.
And to be specific, just so I'm following, so here's just sort of an axon of the roof skin element, right? And when you're saying 8x8, you've taken your image, you've tiled it. So it's in an 8x8 configuration, and then you've taken that and you essentially applied that over here onto the skin. Is that right?
Exactly.
But what you're saying is you guys ultimately decided to go with this 4x4. Is that right?
That's where we are today. Yes. And so that 4x4, what that gives us is, again, it's that read at the various distances. So that's what you'll see in some of the renderings as we kind of flow through the next slides.
Okay.
And so here, really what we're showing, it's just simply kind of looking at the pixels to the panel. And so we're seeing the image tiling of a 2x2 on the left, 3x3 in the middle, and a 4x4 on the right. And these are just kind of looking at this. You see the overall image stretched across the bottom. You see the axon, and then above you see kind of a zoom in look. And so this goes all the way to an 8x8 tiling is what we're showing. Okay. So the next slide, when we talked earlier in the week, we talked about, with this tiling, is it going to be visible on the skin, and if so, how much? And so I just wanted to show here, so you can see this is just kind of a rendering of a portion of this entire project that we're kind of see this image going across. And if you flip to the next slide here, I've just kind of indicated that's where we're seeing one of those 4 tiling. That's one seam between the image right there.
Oh, gotcha. Okay.
And so even though it's going to be tiled, there will still never be an identical triangle to another one because of the position, the way they're rationalized across the surface, and the way the perforation pattern is kind of floating, irrespective of that overall structural diagrid. So yeah, if you really know where to look, you could probably see the seam, but it's going to be hidden fairly well. So
yeah, it is hidden really well.
Yeah. Okay, so we have a few minutes left, and I thought I would talk a bit about the process here. And so, there's a question earlier about, what kind of applications we're using and the tools we're using. To step back, one level maybe beyond that, thinking about the process that we're, file to fabrication, and kind of understanding what we're trying to achieve here is we want to work in a way that allows us to deliver this project potentially without having to do a bunch of drawings that we're passing back and forth. And there's some specific reasons for that. I think it helps us with the workflow. It can be a little more fluid. We're really leveraging the availability of the fabrication shop in this manner. But essentially what we're trying to do is, if we go to the next slide here, everything that we've rationalized with the geometry, we're extracting that panel data. So we talked about, we started in Rhino and Grasshopper, and we've kind of rationalized the panels themselves on the ZEPS system, which is the Zaner system, and they had some help from Studio NYL to kind of lay the ZEPS system within this overall kind of structural grid. So we're extracting that panel data, and we're getting essentially a text file that contains all the coordinates for these panels.
That's right. So when you say you're extracting the panel data, you mean you're extracting the endpoints of each panel in 3D space, maybe plus the centroid of each panel, right?
Yeah, exactly. So that we have the data that we can take that we've extracted, that then we can feed into another application, or even the same application later on, and essentially recreate the same scenario.
Okay. So you're sending XYZ points for those, those 4 XYZ points for each panel.
Yeah, essentially.
Okay.
Okay. So then the next thing we're doing is we're trying to generate the raster data, and so that's what we explained earlier, is taking this image that we've rasterized and applying that to these panels that we've rationalized across the surface. And so you can see here that that upper left image, we're taking that JPEG, and that's where we bring that extracted geometric data in the text file. And we combine that with the image in Visual Studio, and that's where we're kind of layering the two together at that point, so that we can map the physical constraints of the panel to the perforation pattern that's going to locate the centroids of all of the center points of all of the perforations.
Okay.
And then the next thing we need to do is we need to take that and we need to map that to a material. And so this is essentially, we're mapping that image to the actual panel itself. And so this allows us to visualize this in the way that we talked about, that will really be more true to the way we actually see something, rather than just a representation. So here we're taking that the information that we've combined in Visual Studio, and we are taking that into 3D Studio Max. And so now we have each one of these triangles. We have the information that we can rebuild those, and we can map the perforation pattern to the individual triangles.
So let me ask you, I mean, the reason you're mapping this to a material is just purely for visualization purposes and maybe for study, or is there something beyond that?
So it's both. It's first for the visualization study. It's going to be required to be able to do that and actually see that in the way it works. But then the next thing is that we have to map the actual perforation information to the geometry also. So the steps that we're using to get to the visualization process are very similar to the steps that we're using to create the information that we can actually build the panel with.
Okay.
And so that visualization, that allows us to start to look at this from the different focal lengths here that we're looking at, so we can start to understand with this aluminum skin, with this particular finish and this particular pattern, by the perforations that we've located with the constraints involved, we start to see something like this, and we can go through, and we did several iterations of that to kind of see all the different effects of the different tiling, the different visual procedures that we did. And so from there, what we set up this process to do was that we could easily start to generate our drawing files. And so as we talked about that information where we were mapping everything to be able to visualize it, we now have the information layered so that we have the triangle located, and we have the information associated with those perforations. So the center point is there, but we also know what the diameter of that hole will be. And so at this point, we could kind of automate the generation of all the drawing files for each of these 70,000 plus panels. which would be a big time saver. And there's been examples of that have been done before. Where people are writing scripts to generate a lot of the cut sheets and a lot of the details for some of the things like this, because in many jurisdictions you're required to have the paper drawings for permitting. However, if we go to the next slide, the way that we anticipate and we are intending to deliver this is, instead of drawings, we're going to generate text files instead. That will essentially probably be a CSV, a comma separated value file, containing all of the information for the panels and the perforations and their location. And that could be delivered directly to Zaner or a fabricator. And they could use that with very minimal processing to take that into G-code to drive the machines to create these individual triangles with the individual perforations for that unique image that we saw.
So let me stop you there. So that's obviously a pretty incredible thing that you guys are doing here, and you certainly make it sound super easy. I assume, though, that you have your fabricator involved really early in the process. You've worked out the details of what kind of information they needed, what kind of format, exactly what data you are going to send, what data you're not going to send. Can you talk through some of those decisions and the process you guys went through to make this pretty incredible thing happen?
Sure. Yeah. So, I think key to this process is that with our studio working kind of embedded with the sports and entertainment design team from the very beginning of this project, and working really closely with the structural engineer, and having the benefit of Zaner come on board, we were able to have early conversations about not only what material we might use, what's available, including the finishing and the feasibility of sourcing the material and so forth, but we could also understand the fabrication process from Zaner's perspective in terms of what they have on their shop floor, what they're able to achieve, and how they can, for instance, there's different ways you could create a perforation. We could water jet cut it, we could laser cut it, we could punch it with a die. So there's all these considerations, and so we have the good fortune of having some people on the team that not only have the computer programming skills necessary to create this and think this through, but people like James Wharton, who was working on this project, he has a lot of experience with robotic manufacturing, and so having people with the skills like this, of which we have a few on the team that have worked in the robotics lab at their universities and done some work like this, we can have a much more beneficial conversation with the fabricator early on, because we can speak the same language, and so we can start to understand, these are people that have had experience with the code used in the shop, and what's running the machines on the shop floor, and so we can better understand how can we best give the most pertinent information with the least amount of kind of noise delivered to the fabricator for a really easy process.
So was it sort of, I would have guessed you guys had some early conversations, the people on your team and the people on their team who knew how to kind of speak the same digital language, sort of put their heads together. And then you guys, I'm guessing, maybe did some iterations on that. Hey, let me send you some data. You guys tell us what you think. And then, they come back and they say, well, clean up your data this way. We need this. We don't need that. And there's sort of an iteration until you fine tune, what kind of information you're sending them. Is that right? Or was it somehow different?
Yeah, no, it's right. It was actually not even as complex as that. Really, it's just a couple of conversations, and we send a couple of packages of data, and Zaner actually did a few prototypes using that information kind of in this process that we've described, and it's really fairly straightforward if you can get the assurance that the data you're sending is clearly and correctly representing the geometry that you intend to design and build. That's really the crux of the process.
And let me ask you this. So this is getting a little bit into the weeds, but still it revolves around the question of how does someone at an architecture firm make something like this really happen at their firm. So, for example, Zaner, theoretically, your client is going to be using Zaner's metal panel system. So, obviously, in many cases, in many projects, you put out your construction documents, you have a variety of bidders, and you sort of decide who's the best, who has the best price and who's the best quality and so forth. But in this case, Zahner gets in early in this process. How do you sort of reconcile that with the project goals and essentially sort of signing up Zahner early in the process? Or maybe you haven't, maybe you didn't. Maybe they were sort of an advisor in the beginning, and then it was still an open bid, and they happened to win the bid. How did that work?
So it's actually it's kind of a step before the latter that you described. So
Okay.
so Zahner was engaged by the client early on for the design assist, under contract to go through this process, but there was no guarantee. So they're working and they're helping to develop this, which is beneficial because even though they're not guaranteed the project, and even though that the client is actively looking at alternatives, which is the reality of something like this, because we all want to get the best solution for the best value, right?
Mm-hmm.
So yeah, it's a difficult thing, and that's a conversation we have a lot, because there is a lot of value that can add to the process when you can bring the intellectual capital of someone who does this at a very high level to early on.
Mm-hmm.
However, from a client perspective, it's prudent to make sure that you do this in a way that you can still have options
Right.
to make sure that you're getting the best value, and that you don't lock yourself into one solution too quickly. And so we've had to kind of balance that, understanding that we've created what we think is a very good process, and it's something that we've kind of solved working with the people that we're working with.
Mm-hmm.
However, we've had to understand all along that this process and the way we're working would need to be nimble enough that we could adjust it and kind of respond later on if we do need to make some changes.
Okay, so just to say that back to you, so basically, someone like Zahner is essentially hired and paid to do the design assist work, and then when it's bidding time to actually bid out the real project and the actual scope of work, then it's open to whatever bidders, and so Zahner would theoretically, in this case, be one of them among others, and then they have the opportunity to win the project or not win the project, that kind of thing.
Right.
Okay, cool, makes sense.
Mm-hmm. Okay, so yeah, thinking about generating these text files, and so we're trying to achieve this, and what we're looking at doing is we're going to build this stadium, and we're going to deliver this skin system without any paper drawings. And so the other key component there to allow this to happen, beyond kind of establishing the team mentality to set it up this way, was we needed to talk with the California Board of Architects and establish a procedure that they would approve to allow us to actually submit for permitting with digital files rather than drawings. And so that was something that we did kind of in parallel with this, is that we created a procedure and a prototype, a very crude kind of interface that would allow us to stamp and seal anything from a Rhino model to a CSV file in a way that could be delivered and verifiable as the document that the architect had stamped and sealed. So we do have the provisions in place to allow us to submit for permitting with no drawings.
Huh. How did you digitally stamp these models?
So essentially, what we did was we kind of looked at what's been going on online for many years, and we're
Yep.
using a unique hash code
Okay.
that's associated with each of these files, and so that's something that that you can use. If you're going to download something and you want to verify that it's authentic, you can compare that hash against what it should be, and if it gives you the green light, essentially what we've created will show the architect's stamp and seal. And if that hash code is not correct, meaning that it could be something as simple as someone opened the file and closed it again or moved a comma, it's going to give you the red lights, and you won't see a stamp and seal, so you know that you're dealing with a file that is either out of date or corrupted or the wrong file. So
Interesting. So sort of implementing some of the, let's say, DocuSign kind of technology into your models, basically.
yeah, yeah, essentially just finding a way to make that appropriate for the architecture architecture profession, I guess.
Okay, so you've taken the project to this level. And many aspects of it, as we just discussed, are really at the leading edge of what people are doing in our profession. Tell us a little bit more about sort of the next things you guys are thinking about.
Yeah, and this is always something that's fun to talk about. So, we mentioned we have some people of some varying backgrounds in the studio, and James Wharton is a PhD candidate in mechanical engineering, and he has kind of brought to the team some peripheral studies into additive manufacturing. So if we go to the next slide here, if you can recall, we've kind of talked about the perforations and the triangular panel aggregation, and we have these 70,000 unique panels. Well, at the vertices between 6 of each of these triangles, if we go to the next page, we have what's called a spanner. And this is something that would be similar to like a spider connection that you might see on like a Pilkington planar system glass or something like that, right? So it's kind of clamping the points of all these triangles together at a vertices. And so if we choose a spanner that can kind of be globally optimized, it's going to be an off-the-shelf product, and it could work at the interface of these panels everywhere over the whole skin system. However, it won't work optimally at all solutions. It has to have enough variability and tolerance built in to accept the different angles that these are coming together at different places on that curving surface. So we could think about, well, if we locally optimize the spanner, we could kind of design something that works specifically for one specific vertice. However, as you can imagine, if we were going to try to manufacture those by traditional means, that would be a lot of spanners that we would have to create. So if we go to the next slide, we can kind of see what we're talking about here. So we've indicated with the red dots, there would be a spanner in each of these locations. And so imagining if we could take advantage of additive manufacturing and look at some things like 3D printing of metal alloys. The next slide will show what's called electron beam melting. And that's essentially using a laser affixed to the end of a robotic arm to melt powdered alloy into place in three-dimensional space so that we can kind of build up layers and create a component by an additive manufacturing process rather than kind of milling it out of a block. And so, what this would allow us to do is to create these custom pieces in a way that that not only would be quicker than creating the traditional process to put in place to cut them out of a die or to cast them or so forth, but we can also use a lot less material to do so. And so the next image, a couple of images show just essentially some studies that James has been doing that we've used to kind of fuel this study into how can we start to optimize our structural components in a way that we can kind of trace load paths and kind of carve away all the unnecessary material so that we're really creating optimized structural pieces. And this is really something that that we're pursuing, and we're getting some prototypes of these optimized spanners printed here very soon, in the anticipation that the next NFL stadium we build might have some 3D printed metal structural components on it.
Awesome, man! Really incredible stuff. Is there anything else that you guys are doing over there? Jesus.
It's fun stuff. I have the honor to work with some smart individuals, and we have some great clients on some amazing projects that we can work on. So
awesome. If I'm not mistaken, I think you told me that everyone who listened in to this, they get free tickets to the opening day at the Ram Stadium. Isn't that right? Something like that.
I think if you told them that, I'll be okay.
There you go. Good. All right, guys. We'll take some questions here. Let's see. I think the question I have here from Dan Anthony is probably a good one here that many architects are probably thinking, and it's more of an artistic sort of question, but I'll ask it anyways. He's curious about how you might better, us as architects, be better about image mapping to actually meet performance characteristics. And tuning an image to give a better shade, for example, at different times of the day, maybe versus considering the image's or the perforations from primarily an aesthetic perspective. Again, that's kind of a value thing, so I guess you could kind of, maybe you value it one way or the other, but I'm just curious if you have any thoughts about how you guys might consider doing something like that, where you can tune the perforations to something other than just aesthetics.
Yeah, we do, and that's that's something that I value personally very much. And so we've actually done a lot of investigation and study into this, and we're doing work on other projects, not this one specifically, but we're doing exactly that. We're kind of taking this artistic brushstroke, or this this water droplet that's this idea, and that image can then be processed, and we're using things like Galapagos for evolutionary solving, within the grasshopper environment, and then even taking that further to use octopus, which allows us to do evolutionary multi-criteria optimization. So we can start to kind of take sometimes these diametrically opposed criteria and solve for multiple criteria at once. And so by using an evolutionary solver, we can kind of tune into the specific location and start to study things like daylight and heat gain, and we can manipulate these images or even create new images that really respond kind of sympathetically with the environment.
Mm-hmm. Awesome. All right. Well, good question, Dan. Thanks for asking that. All right. Well, I'm going to go ahead and close it up there. So thank you, Heath, for sharing your amazing project with us, and thanks to all of you who've tuned in and who submitted their questions today. If you'd like to attend our next Super Simple broadcast on December 7th, where we'll feature Marc Fournier from The Very Many, he's going to talk about 2 similarly incredible projects. You can register for that episode at blackspectacles.com/podcast. To learn more about our software tutorial curriculum, you can go to blackspectacles.com, where you can try out some of the free course videos. So please let us know what you think and share any suggestions you may have. I promise we'll read every word that you write and use them to tune our next episodes. So thanks for watching.
Thanks, Mark. Thank you, everyone.